Welcome to lecture 14. This is our last lecture on mechanics, wrapping up Unit 2, Mechanics 2. We have a bit of an intermission to bridge our discussion of mechanics to our coverage of laws of physics in the second half of this class, and you will see that in the next lecture set. So, in this lecture set, we are covering fluids. We start with an overview of Chapter 7, noting that the textbook chapter is more detailed than what you have to know for the purpose of homework and any required assignments in this class. We will try to match the level of detail in the textbook in this lecture, so you will see some things in this lecture that you don't really have to know for homework, but I hope you will still find it interesting. The next three sections, Intro to Fluids, Intro to Density and Pressure, and Pressure due to weight of fluids, are lectures that I am borrowing from my Physics 4A. These are the conceptual bits of the fluid lecture from that class. And we will wrap up with the brief discussions of the buoyancy force and Bernoulli's principle to cover the topics that you will see in maybe one or two multiple choice homework questions. These are the basis of some interesting effects that we unfortunately won't get to cover in detail. That's it for mechanics. We start with the Chapter 7 overview here, and I hope to see you for the intermission in the next lecture set. Hi, this is the overview video for Chapter 7, Fluids. This is a chapter that we won't spend a lot of time on. In terms of homework, there are a few mostly conceptual questions. So your textbook actually goes into more depth than we would require you to. But since all the material is there, let me lecture in a way that tries to match the level of detail that your textbook goes in. I think for a lot of the lecture videos, I will borrow what I have from Physics 4A. A lot of it is still conceptual. And I will newly record some items that involve a little more math, but I'll re-record it more conceptually. So, fluids. In the chapter, we start by covering the fundamental concepts of what fluids are, for example. And I think the textbook definition is a little more technical than I was expecting it to be. Yields to shearing forces. I like to think of fluids as liquids and gases, states of matter that flow. Water is a fluid, air is a fluid. And while we are talking about phases of matter, you might have heard about the three phases of matter in a previous science class: solids, liquids, gases. Solids are what we have been dealing with up till now, even through rotation, rigid body motion. And with the liquids, you can say that liquids have fixed volume, changing shape. Fixed volume as in liquids don't compress or expand all that easily. But if you put it in a container, it changes shape because it yields to shearing forces as a fluid. And gases, it keeps neither fixed shape or volume. Whatever container you put in, it's the shape the gases will have, and the gases will expand to fill the volume of the container. And there are other more exotic phases like plasma. We're not dealing with any of that. These three basic states of matter that you probably learned in high school, still what we are dealing with. And what we are covering in the fluids chapter officially deals with the liquids and gases, but a lot of the things that we'll talk about will really lean heavily on liquids because we are going to assume that the fluids that you are dealing with are incompressible. But some of the other examples, like atmospheric pressure, will involve gases. The last of the fundamental concepts is density. It's represented using Greek letter rho. In the following lectures, you will see what the shape of rho looks like. It looks almost like a P, but the way I write it in a way it shouldn't be confused for a lowercase p. And density is defined as mass per volume, mass per unit volume. So the unit of density is kilograms per meter cubed. The SI unit of mass, kilograms, per SI unit of volume, meter cubed. And the cubic meter, it's a surprisingly large amount of volume. You will see that with the demo in the lectures. One good number to remember in terms of density is in the kind of chemistry unit, what you might have seen in previous science classes, the density of water is 1 gram per cubic centimeter. And when you do the unit conversion, it ends up being 1,000 kilogram per meter cubed. I tell the whole story in the lecture following. Look at that. And I guess there's a term called specific gravity. I will never use it, although I think this goes to kind of intuitive way people think about density of various objects. When something floats on water, it has density less than water. If something sinks in water, then it has density greater than water. So this specific gravity will relate to that. And I think a lot of people have great intuition for it. Like if an object, when you put it in water, if it only sinks like halfway, 50% of its volume, and I ask you, what do you think the density of the object is? You might say it's 50% of the density of water, so I guess 500 kilogram per cubic meter. That's what a lot of people would intuitively say, and that ends up being the correct answer. So if all of this describes you, great. I want you to lean on your intuition. So having introduced the fundamental concepts, we introduce these fundamental concepts so that we can do with the fluids the similar things we did with the solid objects. We want to be able to analyze the forces on it and talk about dynamical quantities that are involved. So under fluid statics, meaning situations where there are some forces acting and nothing's moving, everything is at rest and remain at rest, zero acceleration. Under fluid statics, we introduce pressure. Specifically the definition of pressure, I think you might have actually seen this way earlier when I was using this as an example of how we deal with the units in physics. So pressure is defined finally as amount of force per unit area. It says perpendicular area, sure, yeah. Force per area. So the SI unit of pressure, Pascal, it's a derived unit. It can be written in terms of other fundamental quantities. That would be the unit of force, Newton, which itself can be written in terms of more fundamental quantities, kilogram times meter per second squared. So Pascal is Newton force per area, meter squared. That's what 1 Pascal is equal to. And it's a scalar quantity. Even though it's related to force, it actually makes more sense in its physical context to define pressure as being scalar. And the direction of force, you get it through the cross-sectional area that's related to that force. Again, this is kind of more in-depth than you will see in homework and whatnot. So let me move on to the other two examples of fluid statics. The next example is covered with the last of the borrowed lectures from Physics 4a, pressure with the depth, or in the lecture what I call pressure due to the weight of fluid. There's a formula for it. You will see it derived in the lecture. It's actually not, it doesn't involve all that much math. It does result in this formula saying pressure is equal to product of three numbers. The h, or height, or depth of the fluid, the rho, density of fluid, times the g, the gravitational acceleration. And there's a derivation that you will see in the lecture. It's actually a pretty simple derivation. Doesn't involve a lot of algebra. And this is a very useful formula. It can be used for a number of things. One being you can calculate the pressure due to the weight of fluid. Depends on fluid weight. And you can actually use this to estimate atmospheric pressure with a couple basic knowledge like a density of air, which is about 1 kilogram per cubic meter, about 1,000th of density of water, and an estimate of how much height of air you have. Like if you squished everything so that there's a uniform density of air for that height. And I propose as a reasonable estimate about 10 kilometers. And with that height, you can derive that atmospheric pressure at sea level should be about 100,000 Pascal. And you will see that in the lecture that I'm borrowing from Physics 4a. The rest of the concepts and examples will cover the Physics 4a lecture with a little bit too much math, so I'm not borrowing those. I'll record the separate lectures using the infographics generated by Notebook LM. But just to preview what's coming up is we're going to talk about Archimedes principle, which is related to the buoyancy force or buoyant force that results in a net upward force. And you can actually derive it through using the pressure with the depth formula. But we won't do that derivation. I'll just describe some of the consequences at a conceptual level. It's called the Archimedes principle because Archimedes, one of the Greek philosophers, discovered it. There's a story associated with it. He was asked to find whether a crown was made of pure gold or not. And after thinking about it, he realized that there's this principle that when an object is submerged in a fluid, then there's an upward force that's going to equal the weight of displaced fluid. And he came out of his tub saying Eureka or Heureka. And there's a whole story. We call it Archimedes principle. It's one of the few things that Greeks ever got right about physics. And if you don't want to use his name, you could call it buoyancy force. But this statement of the principle, it's I think pretty easy to remember that when an object is submerged either fully or partially, there's an upward force on it, and that force is equal to the weight of the displaced fluid. This both covers when object is fully submerged in fluid, then the volume you would use is the entire volume of the object. It also covers when it's only partially displaced, then the volume you would use is the volume that you are displacing the fluid by, the portion of the object that is under the fluid level. And using the idea of density, you can through observation of whether something is floating or sinking, figure out if something has average density that's less than that of the fluid or greater than that of the fluid. And I'll talk more about that in that separate lecture. So that covers fluid statics. And in fluid dynamics, there's really one principle that I will ask you anything about. That's Bernoulli's principle that's covered in the textbook, section 7.8. And I guess if you are skipping to it, then the main thing to remember is that it comes from conservation of energy. That's really the main thing I want you to know. Now, in the textbook, again, the textbook goes into more detail than we would require you to cover. So in the more detailed section, in section 7.7, we talk about flow of a fluid. That's part of the fluid dynamics. And when we are talking about flow of a fluid, there's two different ways we can talk about how much fluid is flowing. We can talk about how much volume is flowing and for a rate per unit time. So this flow rate specified as a volume per unit time would be like a cubic meter per second. And as something is flowing, you can also talk about how fast, how quickly, what's the speed, and like a fluid velocity, just like a velocity of any object. You can take a fluid element and think about how quickly that element is moving. And that velocity, this is lowercase v, is related to the flow rate, Q, by this formula. You can check that the units work out here. The unit on the left-hand side is cubic meter per second. The unit on the right-hand side, V, that's a speed, so that's a unit of meter per second. And the unit of area, the cross-sectional area, is meter squared. So when you have meter squared times meter per second, you get meter cubed per second. So dimensional analysis is a really powerful tool that allows you to make sense of new expressions like this. And as you look at this flow rate relation to velocity equation, what you might realize is it depends on the cross-sectional area. So if you imagine fluid flowing through like a series of pipes, it's coming from a wider pipe going into a narrower pipe, then if it's flowing at a constant rate with an incompressible fluid and all that, then you can come up with a kind of an expression for how the velocity, speed might be changing. If the area gets narrower, then almost counterintuitively, because the same amount of volume still has to flow, if the area gets narrower, then fluid speed will actually increase, so that the same amount of volume still flows. And this, what's sometimes called the equation of continuity, expresses that. The cross-sectional area times the fluid speed is a constant. It doesn't change from one point to another point. And this holds under the assumption that there's no sink or source. You're not taking any of the fluid away or putting more into that particular volume, and the incompressible fluids, that the volume can't be compressed in one part. And as I said, paradoxically, as the area decreases, speed increases. But if you ever played with a garden hose, then you might have this experience. If you want the water to come out faster from the end, you actually make the end of the garden hose smaller, not wider. So hopefully, after some thinking through, this still matches with your intuition. So both of these, flow rate and equation of continuity, they talk about fluids flowing, things changing, and that's where Bernoulli's equation comes in. There's an expression that you can build that I'll talk about in the other lecture. There's an expression you can build that remains constant from one point in the fluid flow to another point. And what that expresses is the conservation of energy. And different terms there correspond to different parts of energy, like kinetic energy, potential energy, amount of work being done. I'll talk about that in the other lecture. But the main thing I want to make sure you remember is that Bernoulli's equation or Bernoulli's principle, it'll come from conservation of energy. And if there are complications that might cause mechanical energy not to be conserved, then Bernoulli's equation doesn't apply as much. Because if your fluid has like viscosity, or if there's turbulence that's going to dissipate away mechanical energy, then Bernoulli's principle won't hold exactly. And applications. Oh yeah, this. Read about it in the textbook. I don't think I'm going to be really lecturing on it. So that's the overview of chapter 7. Again, the textbook chapter goes more into detail than we would ask you to cover, as reflected in the homework questions and as you will see in the timed assessment. That's because this is coming at the end of Unit 2 Mechanics 2, and we feel like we have covered the more important things earlier, so we don't want to take too much of your time in this last topic that we do have to cover, but we don't want to put a ton of time into covering. So take a look at the textbook to the degree you want to, and just to make sure that what you are required to know is reflected in the homework. Thank you. And it's really very basic things about fluids that we want you to know. So let me just do a quick introduction and introduce some of the ideas that we need to formally talk about to start talking about fluids. And we might have been referring to this from time to time earlier. I know I've definitely done that for one of them. So two main ideas that we are going to introduce are something called density and pressure. And well, I think I've actually mentioned both words before. And it was sort of before we had proper physics definition of both of them. So we will actually introduce them now. So you might already know this, which is, if you do, great. If not, now is when we actually cover it. So I like to introduce those concepts of density and pressure this way. It's a sort of an explanation of why we are now taking time to talk about these quantities after an entire semester of never really dealing with them. It comes down to how you work out the mechanics when you are dealing with the fluids. So does everyone here have an idea of what fluid is? What are some examples of fluids? Water, that's what doctors talk about when they talk about, drink plenty of fluids. So water is an example of fluid. There are other kinds that we call fluids in physics that doctors wouldn't think of as fluids. Any liquid, yeah, oil, alcohol, acid, whatever. So any liquids, anything else? Gas. Also gas. So when we say the word fluids, we are really talking about two phases of matter, liquid and gas. So That's what we collectively call fluids. And it's really, the word fluid sounds like something that flows, right? Well, liquids and gases are what flows. Solid like this, it can roll, but it doesn't really flow. So anything that's solid is not a fluid. Anything that's liquid or gas is a fluid. So when we are dealing with the solids, you know how the mechanics works out. We have dealt with them before. So, this box might be a typical representation of a solid. You know how we apply a force on it, and by applying force, we can move it around, right? Wow, you can't really read the letters, huh? So you know how when I apply force on it, the acceleration you see is related to the force I'm applying. That's Newton's law. That's what we spent a good chunk of the semester on. And what we spent about a third of the semester on is what happens once we start including rotation. So that's when you now worry about torque. So if I enable rotation and I pull a corner of it, then there's a torque due to the force I'm applying relative to this corner. So you see it rotate, or if I, oops. So this is how we've been dealing with the solids. You apply a force and that exerts some kind of torque, and you know how to analyze all of that. So our motivation for introducing the ideas of density and pressure is we want to use these same methods to handle fluids. As in, we want to have some kind of Newton's law. We want to describe how when you apply force on a fluid, how that accelerates the fluid. But the moment you start thinking about fluids, you will see that we run into a bit of a problem. Let me illustrate. So I'm going to cut out a little section here. It might be because I set the property thing, and that might have tied the whole object together. So when I liquefied it, it liquefied the whole thing that shared the same property. So now let me liquefy just this portion. Okay, good. Let me turn the color so that it's easier for you to see. Maybe something like that. All right. Yeah, I think those things were these are actually solids. So once it's a liquid, then you see that it doesn't move the way it used to before. As in, if I try to drag any portion of it, the program doesn't let me for one. And so, I can actually, draw a tool for myself and use this tool to splash around the liquid. And, when you see this liquid splashing around, the way it moves it's quite different from how a solid object would be affected. So let me get rid of this. I don't really want them. Yeah, I'm kind of new to this program, so each time I learn something. Okay, so if I take this and when I lift it, the water, it kind of moves out of way, right? So I can splash them, but they don't really. If I try to describe this water, this liquid, like I was describing any other solid object before, either using Newton's law with the translation, or even if I were to include rotation, it really comes down to the rotation. We call it rigid body rotation, and this liquid is by no way rigid. It changes shape constantly. In fact, in your science class, you might remember that was one of the property of liquid, that it takes the shape of the container, and if it's gas, it also takes the volume of the container. So we need to have a different paradigm to handle mechanics of this fluid, mechanics of liquid, but I don't want it to be completely different, because I feel like all the laws of physics we need, we have already introduced it. And we want to simply modify it very slightly. So, by laws of physics, really this is what I mean. The biggest thing I mean is Newton's law. So Newton's law says
net force is equal to mass times acceleration, right? And I really want to be able to use this with the fluids as well. But the problem that I run into is that there's no, I guess, distinct mass that I can talk of. Because if I was handling this solid object, then there's a distinct mass that I can talk about. It's the mass of the entire object, right? But when I'm dealing with this liquid, its shape is constantly changing. When I try to apply some upward force, the kind of portion where I'm applying upward force is changing, right? So this is where the challenge comes down to. How do we modify this expression here in a way that we can apply to this new type of object that doesn't have a fixed shape? It's always going to be changing shape in response to force. It's never going to have a one rigid shape that we can handle like we have so far. So as you're thinking about let me give you one hint. This is the reason I like to use this simulation. Because actually the way the simulation itself handles a liquid actually reflects how we are going to handle it in the way we do it analytically. So, look at how the simulation handles a solid object, like a solid sphere. And, so you'd agree that everything you see in the simulation seems realistic, right? This representation of liquid, it looks liquidy, right? That's how you would have expected the water to behave when it's being bumped like that. So this simulation, so solid is kind of easy to see how it's simulating this solid object. Now I want you to pay closer attention as I move this around and notice how the simulation is simulating liquid. How do you think a simulation is simulating liquid? Like in what way is it treating liquid differently than this solid sphere? Isha? Yeah, like a collection of particles. Because this is a crude simulation, you can actually see those discrete units of particles. As it splashes around, you'll see that it always comes out in these discrete spherical things. Like that's the smallest unit of liquid that it's simulating. And the way the simulation handles it is it has some kind of a mathematical model for repulsion between those spheres. So if I suddenly apply a force, those spheres can kind of compress. But after some compression, they repel each other, so that's where they bounce up and down. So that's how the simulation is handling it. It's essentially working out those interactions to describe liquid faithfully by taking this liquid and dividing it up into, okay, I'm gonna get tired of drawing it, so let me just do this. By dividing it up into tiny little pieces. So each little portion here is what the simulation will use as that's our block of liquid. Then the simulation can, using the surrounding object, calculate, okay, what kind of force is on it. Then in response to that force, it'll use however much mass this has, and it'll use Newton's law then to sort of calculate what the acceleration should be, and based on that acceleration, it shows you all this motion that you see. So that's the approach we are going to take as well. The difference is that, in this numerical simulation, it has to do it in a discrete way. It cannot, take an infinitesimal amount of liquid because they'll take way too much computing power. But when we are dealing with the real world, these water molecules are super tiny compared to any macroscopic object. So we are going to imagine making this division infinitesimally small. As in, I have this particular sort of length element. That's going to be an infinitesimal. If I take any particular block of water, then it's going to be described by what's called volume element. That would be simply, dx times, let me call this y, dx times dy times dz. That'll be the volume element. And that's kind of exactly what it sounds like. It's the amount of volume in this tiny piece of fluid. And we are doing calculus, so you have to imagine that this piece can be as small as arbitrarily small. There's no limit to how small it can be. So this is the context where we want to introduce the new-ish concept of density and pressure, because these two ideas will help us express the mechanics involving this little fluid element. Okay? So let me just introduce density and pressure, since that's the quickest way to introduce it. So most of you have seen density, but let me write it down. So this is how in physics, we define density. Density is, so if you have a particular material, like these standard masses. This is a 500 gram mass. This is a 200 gram mass. And it has some amount of volume. You can either calculate it as a cylinder or whatever. So it's some object with some amount of mass, 500 grams, and some volume that you can imagine measuring. And density is defined for that object as mass per volume. Right? Why would this be useful in trying to describe a fluid in this way? Why would it be useful to know the density of a fluid? How does that help you describe the mechanics of, for example, this fluid element? Stephen?
Tells you the mass of each individual cube.
Yeah, it tells you the mass of this individual cube. So, you are going to parameterize the fluid element so that you are describing in terms of this volume element. And when you try to describe the mechanics of it, you are going to need to know the actual mass of that element. And the way to describe the mass would be that small amount of mass for this element is the density times the volume element. Let me, I think we have mentioned it before, but in case we haven't, reintroduce the symbol for density. This is the standard symbol for density. It's a Greek letter, and I want you to make sure everyone knew what this letter was. Everyone here knows the name of this letter? Rho, right? Anyone here speak Russian or know Cyrillic alphabet? Okay, so that doesn't help. Because, to a lot of the Roman alphabet people, this looks like a P. But if you knew Cyrillic alphabet, then you do know this. Actually, Russia, when you write it in Russian characters, this is the first letter you will see. This is the R kind of sound in that alphabet. And so, this is the letter we call, it's the Greek letter called Rho, and it pronounces like R. It looks like P, but it pronounces like R. And I will tell you that my Rho never looks like my P. So, it's a lowercase thing. And this is my lowercase p. There's always a sharp corner here. My Rho is always rounded, written with one stroke. So it's a distinct letter. It's the standard letter we use for density. So to express the amount of mass in this little element here, we would say that's the density of fluid times the volume element. So this will give you an expression for density, and depending on the situation, you can do the rest of the calculation. Maybe you are simulating something like this. So, but yeah. We need to talk over one thing about density. It's sort of a distinction between density and mass. It's especially useful when you have two different objects. that's made up of the same material. This is made up of a steel, I think, or some kind of ferromagnetic stuff, because I'm pretty sure this magnet will stick to it. So yeah, it's some kind of ferromagnetic stuff. Let's say iron. So it's made up of iron, and when you look at mass of these two objects, they have different mass, right? 500 grams, 200 grams. Now, intuitively, do they have the same density? So I guess this is how you would think about it. So density is defined as mass per volume. So if for a given object, if you imagined having twice the material in volume, and if you can convince yourself that, yes, I would have twice the material in mass, then it means the density of that object, whether you are talking about this density of this object or density of this object, they are the same. So what does your intuition tell you? So you already know that this is 2.5 times the mass of this. Does it look like about 2.5 times the volume? Roughly, right? Yeah, and this is our common experience, that if we are talking about mass, that's a property of an object. You get a different object, it'll have different mass altogether, even when they are made up of the same material. But density is something that people identified early on as it's the property of the material. It's the property of iron. It's a property of water. If you get some amount of water, so let me try to get 500 milliliters of water. So if I get 500 milliliters of water, then the water has a certain amount of mass. That's going to be related to how much volume, 500 milliliters, there is. So, if I got twice as much water, 1 liter of water, then it would have double the mass. So, chemists from early on started measuring this density because they realized that different substances have different densities, usually. And for a given substance, under a range of different conditions, the density doesn't really change. So, so density of the iron, is it greater than density of water? Or is it less? Greater? How do you know it's greater? You have this experience, right? You put it in water and it sinks. Well, I don't want to break anything. All right, if I break the beaker, then I break the beaker. Okay. You put it in water and it sinks. Or density of wood, is it smaller or greater than water? It's smaller, right? And a lot of times people say colloquially that wood is lighter than water. But when you say that, it's sort of like, okay, lighter than how much water? It is heavier than a drop of water. But if you are comparing this to the same volume of water, then it is lighter. And one of the things that you know that from is that it floats on water. And we'll talk about how that relates to the density actually being small. But so this is a density of a material property that you can actually build a table of. So we wouldn't bother making a table of masses because you shave off a little bit of material, the mass just changes entirely. But with the density, you shave off a little bit of material, density doesn't change because it's the property of iron. So let me pull this up before it starts rusting. So in your textbook, you will actually find the table of densities. And there are some numbers that are actually useful to know. And I want to talk about density of one substance in particular, and that's water. Anybody here know density of water?
1,000.
You might tell me the version that you heard in chemistry class. Because when I hear 1,000, I think that's the one you saw in the physics textbook, which is great, but it doesn't tell the story I want to tell. What's the version you heard for the density of water in your chemistry class, or some really convenient number that you might remember? 1? Maggie, were you saying 1? Yeah, so 1 is the correct number in the correct unit. So what is it in units of? It is 1 what? Gram per cubic centimeter, right? So this is density of water. It's almost suspiciously convenient. Anybody here know why density of, why it's so suspiciously convenient? This is more of a science history trivia. It doesn't really relate to anything today, but it's a story that if you remember, it'll help you memorize what the density of water is. So it'll help you anchor some typical values of density. No one here knows the science history? Like why density of water came to be exactly or almost exactly 1 gram per cubic centimeter? Asia? No? Yeah, it's by definition. This is how we originally, hundreds of years ago, this is how we defined the gram. Gram used to be defined by property of water. So the way scientists, I guess it might be alchemists or chemists, whichever, people doing science then defined the unit of gram, which is unit of mass, by the property of water. They were super careful with it. They specified the standard conditions, like water at 1 atmospheric pressure and some temperature, because they discovered that when you change the temperature, the density of water changes. So with all those caveats, this is how gram is defined. Gram is defined so that it's amount of mass when you have 1 cubic centimeter of water. People had defined the centimeter earlier, so they knew how to measure cubic centimeter. Or if you remember your volume units, 1 cubic centimeter is also 1 milliliter. So you might have some beaker that can actually measure out milliliters. And so they knew if you measured out 500 milliliters, like this is how you would define 500 grams. So, we don't define grams that way anymore. We have much more, because, the measurement technology improved a lot. We can measure masses in like 1 part in a billion. And at some point, defining gram by property of water becomes limited by the property of water itself, as in how pure can you get it. So we stopped defining gram by water. And today, gram is actually, kilogram is defined by a standard kilogram that lives in France, never sees light of the day. Copies are made of it to get shipped to elsewhere. That's the SI kilogram. And in the very near future, they are actually going to change the definition of kilogram again to base it on something called Planck's constant that's important in modern physics. So that's how we are doing it today, but this is the history. And whenever we redefine these units, we always redefine it in a way that we don't have to change the general idea of how much 1 gram is. So if with the current definition of gram, it still works out that density of water is almost very nearly 1 gram per cubic centimeter. Now, some of you are telling us 1,000. So 1,000 in what unit? It can be correct if you have correct units. So Abdi, what's your unit for saying that the density of the water is instead of 1, saying that it's 1,000? 1,000 in what unit? Yeah, that's the basic SI unit of mass and volume. Kilogram. It's the weird one. It has kilo prefix, but that's actually the base unit. Kilogram per. The base unit of length is meter. So cubic meter would be the base unit of volume. And does everyone here know how big a quantity a cubic meter is? Like how many? So everyone here has some idea of what liter is? So if we are comparing liters to cubic meter, we are comparing liters to cubic meter, which is bigger? Cubic meter is bigger by how much? So let's say 1 cubic meter is equal to some number of liters. 1,000 liters? Everyone agrees that sounds about right? 1,000 liters is 1 cubic meter. Let me show you what 1 cubic meter looks like, because I think this is one of those quantities when you see it for the first time, you think that's too large, that can't be right. But this is actually right. So let me help you visualize with my meter sticks. So let me get 3 meter sticks out. So this is to visualize a cubic meter. So this is 1 meter. If you're talking about square meter, we are talking about an area with 1 meter on a side and 1 meter on the other side. It's a pretty large area, right? It's about an area of this half of the desk. And if you're talking about cubic meter of volume, you have to imagine taking this area and stacking it up to be a meter high. Is this a fairly big volume? It's a pretty good sized aquarium. Like, I don't have room for anything like this in my room. But if you have a good sized aquarium, it might take about a cubic meter for aquarium that's at home. So, and think back to how small a liter is. Big bottle of soda that you might get is 2 liter bottle. And imagine fitting 500 of those in here. Like, you can imagine that, right? Yeah. So this is what I want you to visualize. That 1 cubic meter, it is a pretty big volume. So it is actually 1,000 liters. And we can show this mathematically too. This is the unit conversion exercise where you do kind of have to be careful to make sure you don't make mistakes. I think the main disconnect here comes down to not many people, at least the first time you see it, have good sense of how many cubic centimeters 1 cubic meter is. So let's say I'm talking about 1 cubic meter. How many cubic centimeters is that? 10 to the power of 6. So give me a number in English. Did someone say a million? Yeah, 1 cubic meter is 1,000,000 cubic centimeters. Sounds about right? Yeah, and if this doesn't make immediate intuitive sense to you, this is how I would convert units. So I will do this up here too, but this is where you have to be aware of scaling factors. So how length scales is different from how an area scales. And it's also different from how a volume scales. So for those of you where this number looks big, it's because you are thinking of, 1 meter, that's not 1,000,000 centimeters. 1 meter is only 100 centimeters. That's what you are remembering, right? And when you want to turn this into volume, then what you are doing is you are cubing it. Take the cube of the left-hand side. At the same time, take the cube of the right-hand side. Then the left-hand side becomes 1 cubed, that's just 1, times meter cubed. That's a cubic meter. The right-hand side becomes, 100 cubed. 10 to the power of 2 raised to another power of 3. That's 10 to the power of 6. 10 to the power of 6 centimeter cubed. And so it comes down to a matter of a scaling relationship. Everyone here familiar with the scaling relationship? Yes, as in, imagine, so I'm just going to give you a fake number. Imagine I'm 140 pounds. I'm not, but that's my ideal weight. If you saw someone like me, except twice as tall and just everything proportionally, how much do you think that person should weigh? If I'm 140 pounds and you saw someone else who's just like me, except it's double in every way. Twice the height, twice the width, twice the depth. How much would that person weigh? 280 pounds? No. That person should weigh 8 times what I weigh. So it would be 8 times 140, so something like 1,120 pounds or something like that. So in fact, if you know very tall people, that's where, like, if someone's like 6'5", even very skinny person who's 6'5" will be like 200 pounds, because very small change in height, if you are doing things proportionally, that goes to the cube. So someone who's 10% taller than you are, their proportional weight should be about 30% larger. All of this sounds familiar? Well, if not, as you do engineering, you'll come across this at some point more, and you'll get familiar with it. For this class, this is what I want you to be familiar with. That idea that 1 cubic meter is a very large volume. So when your math gives you that 1 cubic meter is 1,000,000 cubic centimeter, which means because of this, it's 1,000,000 milliliter, which means it's 1,000 liter. That's actually the correct answer. It sounds like a lot of volume, and it's because it is a lot of volume. Okay, so let me just do this quick unit conversion here that gets you this 1,000 kilogram per cubic meter. This is, I assume you have seen a lot of this in a chemistry class, but in case you haven't or you forgot, I'm not supposed to assume you took chemistry for this class anyway. So let me just show this one unit conversion. We don't do a lot of unit conversion in this class, but density is, I think, one example where you should know how to convert unit. Because it's just so much simpler to remember that density of water is 1 gram per cubic centimeter. But for any calculation you do want to convert it to basic SI unit. So I want to convert this eventually to kilogram per meter cubed. And the technique you learn in chemistry, hopefully, is you multiply by 1. In each step of unit conversion, you are multiplying by a ratio that works out to be 1. It's just that it's a convenient combination of units. So you cancel out the unit you don't want, and you gain the unit that you do want. So I'm going to multiply by a ratio that will have unit of kilogram per gram. So if I want this ratio to be 1, the quantity on the numerator should be the same quantity as quantity on the denominator. So think through it for a while, and you should get 1 kilogram is equal to 1,000 grams. So this ratio is 1. Everyone agrees? Yes? So multiplying by this shouldn't change anything, except for the fact that I'm going to get rid of grams and gain the kilograms that I wanted. So that's one step. Now, if you're just looking at this, you might say, oh, so density of water should be, 1,000th of kilogram whatever in the basic SI unit. There's the second step. I need to convert the unit of cubic centimeters to cubic meters. Here, the way I like to do it is actually this. So, if you remember this, that this is 1,000,000 cubic centimeters, great. But suppose you didn't remember it, then the way I would do it is I would say, all right, so multiply by, so I want to cancel out centimeter and gain meter. So the ratio I'll be using is 100 centimeter per meter. But single factor of this is not enough, because I have 3 factors of centimeter. So I need to raise this to power of 3. And when you do that, you remember to raise 100 to power of 3 as well. So when you work out the numbers, it's 1,000,000 divided by 1,000. That's how you end up with the basic SI version of 1,000 kilogram per cubic meter. Good? So that's the long bit about density. That's the density of water. And oftentimes what we do is, if you want to describe density of any object, the convenient, intuitive thing to do is compare it to density of water, because that's sort of the familiar quantity. Like if you want to know density of a person's density is about the same as water. That's why you just about barely float. So, my density, including bones and everything in me, is about 1,000 kilogram per cubic meter, maybe slightly less, because I do float. If you are looking at density of something like a steel, I forget, it's like 5 times or some number times density of water. That's why when I drop it, it sinks in the water, it doesn't float. Good, everyone okay with the density? All right, so that's 1/2 of trying to describe the mechanics of all of this in terms of this tiny fluid element. Now, that only takes care of only one side of Newton's law equation. I have to know how to handle the other side, the one that has a force. Because, this is what you see. When you are applying some amount of force, let me get this out of the way. Oops, All right, that's good enough. Sorry, I meant to get this out of the way, but all right. Put it here. I might need more water. I don't know how to increase the amount of water without. All right, let me just stop it here. So, imagine lifting this mass here. And hopefully your intuition tells you that how much force you have to exert to lift this up, to lift some amount of water, it's different depending on how much water you are lifting, right? So, if you are using a bigger piece, oops, I didn't get a bar. All right. Okay, so if you are lifting a bigger amount of water, then as I lift this up, because I'm lifting bigger amount of water, the force I have to exert is bigger than if I lift this smaller piece, lifting the smaller amount of water. Then the amount of force I have to exert to lift this amount of water is smaller, right? So if we try to describe this in terms of force, we are going to have the exact same problem we did with the mass. So we have to do the kind of the same thing that we did with the mass, where we imagine breaking this entire mass down into tiny little pieces so that we can describe the mechanics of this small fluid element. Now, what we want to be able to do is we want to be able to describe the amount of force on this small fluid element. And I guess the easiest way to think about it is think about it in terms of this entire container. So as I lift this container, I am applying some amount of force, right? You can kind of see it there, about 100 newtons. So I guess this is the question I could ask. How should I be dividing that 100 newtons? Do I divide that 100 newtons per volume of the mass, 100 newtons per something, right? And once again, because it's easier for me to just give you the answer, let me give you the answer. The way we divide up that force is we divide it up by this cross-sectional area. So it's not force per entire volume. It's a force per the cross-sectional area that will give you some way of describing mechanics of this fluid in terms of this little fluid element. So let me write that down. That's going to give us the definition of pressure. Pressure in physics, not social science or whatever, is defined this way. It's defined as amount of force per area. So imagine you have, imagine you want to describe how much force is needed to have this element of fluid suspended in fluid. Then what you do is, all right, let's figure out the bottom surface area. And if I know the pressure, so let's say I know the area here, dA is the dx times dy. That's my sort of area of this element. And if I know the pressure down here, if I know pressure, let me just call it capital P, then I can relate this pressure to the amount of force on the bottom surface of this element. I can say on this object, there is an upward force. There's an upward force that can be described as pressure times the area. So this is how we describe sort of the infinitesimal aspects of fluid, so that at any given time we can imagine taking the fluid, breaking it up into smaller pieces that we need to analyze it, and then we can describe if we know the pressure, then for each one of these elements we can describe the amount of force on it by taking the pressure and multiplying it by area. And once you know the force, and once you know the mass from knowing the density, then you can talk about Newton's law for this little tiny element. You can say, trying to use Newton's law, you could say the net force on that element is the amount of mass times acceleration, and these can be rewritten in terms of the pressure and area. So the left-hand side would look like the force would be pressure times the area element, and the right-hand side would be this density times the volume element times area. And we are not going to do much with it except for maybe at some time during the lab section when we go over Bernoulli's principle or some kind of a derivation of Bernoulli's principle. But so this is the approach to dealing with fluids. If you ever had to actually deal with it, this is the basic mechanical approach to it. Yeah. What I want to point out the rest of today is some of the interesting facts to know about fluids. And the biggest is, I guess, what we call pressure due to weight of fluid. And this is the demonstration for it. This is the demo I used to illustrate pressure due to weight of fluid. You might have seen it. It's just a simple column with 3 holes in it. And let me first fill it up with the water. And so it's just a column of water. Now the interesting part is when I uncork these holes. When I remove the corks from each one of these holes, watch what you see. So let me try to remove them all at the same time. Do you see the water coming out at different rate? And why do you think that is? So water is coming out the side sort of perpendicular to the vertical wall, but how fast the water is coming out down here is different from how fast the water is coming out here. Yeah, more force, more pressure. Like you talk about your water pressure in shower or whatever, right? This is the exact same thing. Where the water is coming out more forcefully is where there's more pressure. So this is something we can actually derive. Based on what little mechanics we know, we can actually derive a relationship between the aspects of this that you can measure and how much pressure there should be here. So let me just put water back in here so that you have a prop to think about as we draw some diagrams and try to think of a way to analyze it. So you have some intuitive sense. There is a pressure at this lower position here, because you see that when I take this off, then the water comes out. And in fact, you can see what it looks like when the pressure is 0. Let me get rid of some of the, so just to do this, you can see this amount, how fast the water is coming out. It gets slower over time. And in fact, when the water comes down to exactly this height, no water is getting pushed out. I mean, at some point it's because water is below, so there's no water to get pushed out. But as it's approaching that, when you barely have just a little amount of water, water basically leaks out. It's no longer shooting out. It's because at this point, there's really no pressure here at all. So, so you can see intuitively some kind of relationship between the amount of pressure at this point and how much liquid is above that point, right? And we can actually express that with these concepts that we have expressed. So let me draw that diagram. So imagine a cylinder of water that at some height. So imagine having this filled up to some height. There's some amount of water. Let's say it's water. So density of water is what you have here. And what you'd like to imagine doing is imagine opening a hole very near the bottom. And essentially what you'll be interested in is, you can put it two different ways. Let me put it first way that relates to what you were seeing there before, the water just shooting out. So the way you can analyze it is you can imagine a small element of water that's here, right? And you can say outside here, pressure is 0. Or it's the same pressure as the atmospheric pressure, some kind of environmental pressure. So you have some environmental pressure P0 outside. And what you can say is that inside here, you have a higher amount of pressure. Inside, within the fluid, we have some higher amount of pressure, P0 plus delta P. And this additional pressure is what's responsible for pushing this element of water out. Because then pressure times this area gives you a force that's pushing it out. Force is this amount of net force, is this amount of pressure times the area. So that would be accelerating the water through. So by the time it leaves completely, it has some velocity with the trajectory that you're seeing. Okay? So that's what you're seeing. So really what you are interested in is, at this kind of a height, how much additional pressure delta P do you have? And you can see intuitively where that pressure is coming from. Imagine this kind of an imaginary surface at this height. Then what you can see within the container that you don't have outside the container is that you have all this water, right? All this water is pressing down on this kind of an arbitrary surface that I just drew up to divide up the water. So it's not actual, there's nothing that actually divides it, but I'm just saying, I'm considering this water below separately from the water above. And the water above is exerting some amount of pressure along this boundary. So we can calculate the pressure. And we can do it easily using this definition of pressure that we introduced. So if I want to calculate the amount of pressure here, then what I need to say is, all right, the pressure P, the pressure is equal to some amount of force that I'm going to figure out in a bit, amount of force divided by area. Where is this force coming from?
Force of gravity.
So weight, right? Force of gravity. So that's the weight of all this mass. So it would be this force would be the weight of all this water. So mass of the water times g. That would be the force. Now, when you write it this way, this mass, it's going to depend on a whole lot of quantity. It's going to essentially depend on how much water here is. So what I want to do is I want to rewrite this mass in terms of some simple parameters that I can measure. So some simple parameters that I can measure are things like the area, the cross-sectional area here. I can measure it once and that'll never change, it's constant. I can probably use density of water. And one single parameter that'll probably be useful is height of this water. Okay? So I can express this mass this way. I can say this mass is going to be the density of water times the volume element. In this case, this volume would be the cross-sectional area times the height. Right? That seems reasonable. That's the volume. So the mass is the density times cross-sectional area times height. Now, when you plug it in, this is what you see. You see a nice cancellation. So amount of pressure along this surface is equal to density of water times area times height times g. Oops, I meant to use capital H. Times height times g divided by area from the definition of pressure. And here you see that the area cancels out. So whether it's a wide container or a narrow container, it turns out it doesn't matter. Because when you are looking at pressure, it's force per area. So if we have larger area, then you have larger area, but you also have larger force because you have more amount of water. So this is a formula that we call, what you get is what we call pressure. I don't think there's a better name than this. It's kind of a long name. Pressure due to weight of fluid. And that's equal to the density times height, or the way we usually write this, density times gravitational acceleration. Density, or I guess density of fluid in general, times g times the height, the depth of the fluid. Good. Now, I'm going to just assert one thing without proving it. Even though we derived this in this specific case of a straight wall cylinder, it turns out this result is valid even when you have sloped surfaces. Like if you had something that looks like regular drinking glass. So, if you have some container that instead of having this, well, let me just modify this side. If you have a container that looks more like this, it turns out that the pressure at this height is still given by this formula, even though you have additional mass up here. How does that work? How do the forces work out? I mean, if you take this amount of mass and divide it by this force area here, then you're going to get greater pressure, aren't you? So, we are not going to spend a lot of time with this. You can read about it in Giancola if you want. But really what it comes down to is when you have this sloped surface, then there's going to be some normal force from the wall. That there's an upward component, so that's helping balance out some of the weight of the water. And the result is that whatever shape of this is, doesn't matter. This is the correct formula for no matter what kind of shape of container you're dealing with. Okay. All right, so that's the pressure due to weight of fluid. And this is exactly what you are seeing illustrated here. because at a deeper depth, there's greater pressure, so the water gets pushed out at a faster rate. Now, one thing might be a bit confusing because so you're used to dealing with the force as a vector quantity, right? So your inclination might be to think of pressure like a force, so a vector quantity. If you look at it that way, this is where it could get confusing, because the pressure due to weight of fluid, it's all pointing downward, right? But the force on this fluid element, it's going horizontal. How come? That's sort of where the opening is. And with a force due to pressure, so actually pressure is a scalar. Pressure is like a temperature. There's no direction associated with pressure. The force does have direction, and the direction of force actually comes from the geometric shape. So imagine you have like a cube. Imagine you have a cube. Then you have different pressure at different sides of the wall, and the direction of the force will always be perpendicular to the surface. So at the top surface, you would get what you expect. At the top surface, the weight of the water will be pressing down. But on the side surface, weight of the water is not pressing down or up. It's pressing perpendicular to the area, so pressing sideways. And here's the most fun part. The pressure on the bottom, or force due to pressure on the bottom surface, it's actually upward. So pressure actually pushes it up instead of downward. It's a bit counterintuitive until you think of it this way. So this is how I like to think of it. Once again, imagine a small fluid element. Imagine a small element of fluid just below my cube, right? And this is what I like to imagine. In what direction would this fluid element move if my object wasn't here? Will it rush in to fill in that gap, or will it stay there? It'll rush in, right? Unless there's like an air gap there, but if it's just vacuum here, this fluid element will rush in. Now, with this object here, it's not rushing in, so something is pushing it out to keep it out. And the force that you get on this surface is the reaction force. It's the force, so this surface is pushing the fluid element so that it doesn't rush in. And fluid element in return is pushing the surface up. Okay? But all of that, I guess it doesn't really matter in the end. The rule that you should remember is that the force due to pressure is always perpendicular to the area where the force is being applied. So when you have a hole that's sideways like this is the area. So the force is going horizontally, it gets accelerated horizontally. And you can see it here. I mean, it's not that surprising. So here it's coming out horizontally. When I angle it up, it angles up because the force is perpendicular to this surface. Yeah. Okay, so quick exercise I want you to do in the remaining 30 minutes or so of the lecture section is I want to calculate some example cases of pressure due to weight of fluid. And I guess we can do the water one right after we do atmospheric pressure, because that's a useful number to know, and until you kind of get used to it, it's actually a surprisingly large number. Anybody here know, so how many here have seen, so let me write down atmospheric pressure. How many here have seen this phrase, 1 atmosphere? What does this phrase refer to? Or what class would you have seen this phrase, 1 atmosphere? You would have seen in chemistry, right? And what this is representing is it's the atmospheric pressure. It's how much pressure is right now in this room in the air. Now, this 1 atmosphere, this unit is sort of defined the way chemists define it, kind of how you measure it. This atmospheric pressure is just all around, and when chemists first invented the barometer, they assigned whatever they were measuring to 1 atmosphere. But it's not really based on a fundamental mechanical concept. So, I never talked about unit of pressure. So, pressure is, force, newtons per meter squared, right? In SI unit system, we actually give a name to this particular combination. Anybody here know the name? This is Pascal. If you are reading through the book, you will have seen it. So this newtons per square meter is what we call unit of Pascal, or if you want to shorten it, PA. Okay? So this is the question I want to ask you, which some of you actually might know the answer to. If I want you to express 1 atmosphere, which I know what it is, it's the pressure right here, but I don't know how much that is in mechanical terms. I'd like to express it in terms of Pascal, so that I have an idea of how 1 atmosphere relates to sort of mechanical aspects. Anybody here know? This might be a number you memorize in general chemistry. At least I did when I took high school chemistry. I mean, if you don't have it memorized, that's fine. Anybody have it memorized? You might have it memorized in kilopascals. All right, nobody does. Let's just actually estimate. We can estimate how much atmospheric pressure should be. We can estimate it using this formula. So we would have to know some numbers. G, we know. G is 10 meter per second squared. So 2 numbers we need to kind of estimate is the density of air, and we need to know the height of air, or some kind of a reasonable measure of how much height would it be if we had atmosphere at a uniform density and it wasn't getting thinner as you go higher up. So let's start out with the density. So density of water, 1,000 kilogram per cubic meter. Does anyone have an intuition when water turns into vapor, when liquid turns into gas, how much smaller the density becomes? Or another way to put it is how much bigger the volume becomes. Anyone here have some idea? Just in rough terms, Does the volume get bigger by factor of 2? Probably not factor of 2, factor of 5, 10, 100, 1,000, million. 1,000. This is a good round number to know. I mean, I don't recommend that you memorize a lot of numbers for this class. These few numbers are ones that are worth memorizing. Density of water, it's worth memorizing. And the second thing that's worth memorizing is the typical ratio of volume of same mass of material in liquid form and in gas form. When a liquid turns into gas, the typical expansion factor is about 1,000. It depends on the material. If it's like helium, liquid helium into liquid gaseous helium, it doesn't change all that much. But something like water, it expands by about a factor of 1,000, which gives us an estimate for density of air. We can say that density of air is approximately 1 kilogram per cubic meter. It's a surprisingly big number when you actually start calculating things. This is what this number means. This is a cubic meter you remember seeing before, right? It's a bit large volume, but it's not the entire room. Within this volume of 1 cubic meter, there's a kilogram of air. So you gather up all the air in this room, it should probably weigh as much as at least the sum of us here. Right? Like, 50, 100 kilograms or something. I don't know how many cubic meters this would be. I don't want to estimate it. Yeah. So air is surprisingly heavy or there's a surprising amount of mass when you gather up enough volume of air. So the last thing we kind of have to estimate is height. And this will be based on your experience or your earth science knowledge. You have to know some reference scales. Like, is the atmosphere, I don't know, 100 meters high? Does that sound about right? No, 100 meters cannot be right? Like you go from sea level to go up a gentle hill, that's 100 meters. Atmosphere doesn't go away in 100 meters. What about a kilometer? Still not quite enough, right? Decent number of mountains are about a kilometer in height. And when you go up there, you still have about the same amount of atmosphere. Atmosphere didn't really go away. How high up do you have to go before you start to notice that my atmosphere is not really there anymore?
$50 kilometers?
50 kilometers, that's in the ballpark. It's in the order of magnitude. And just because I know the correct final answer that I'm trying to get at, I will give you a number that will get to that answer. So about 10 kilometer is about the closer ballpark number of if you took all the atmosphere and squished it down so that it's the same density throughout the height, it would be about 10 kilometers. And the way you can remember it is, that's more or less the height of the Mount Everest. Or that's more or less the height at which airplanes fly. And that's the height where, up until recently, people thought you couldn't climb Mount Everest without oxygen tank. There were people who actually did it in the recent years without any oxygen tank. But in the past, we thought there's not enough air there, you need oxygen tank to survive. And if you are in any commercial jetliner which flies at this height, the cabin is pressurized. If somebody ever opens the door and there's explosive decompression, the first thing you notice is that you can't breathe anymore. That's why that mask thing drops down so that you can breathe. So this is about approximate height of air within the order of magnitude. So let's see what we get when you plug in these three numbers. I better convert this to meters because kilometer is not the basic unit of SI thing. So it's a 10 to the 4 meter. So, these are all nice numbers. 1 times 10 times 10 to the 4. 10 to the 5. Make sure the units work out. So meters squared cancels out. You know what? You can work out the units. It's going to be Newton per meter squared. So it'll be pascals. And so 1 atmosphere is about 10 to 5 Pascal. Doesn't really strike you how big a number that is until you estimate some amount of force. I was having some of you do this demo, and you can play with this after class if you want. This is the demo I got about a year ago to illustrate the strength of atmospheric pressure. This is nothing special, it's just a rubber sheet. The only thing that's special about it is there's a handle attached to the middle so that I can apply a fair amount of force without lifting a corner. Because when I lift a corner, then I'm letting the air flow, the pressure is equal on both sides, they kind of cancel out. When I lift it from the middle, what I'm doing is I'm trying to overcome the atmospheric pressure with my own force. Because there's no air underneath to help me lift it, so it's all my own force that's doing it. And you saw me briefly try to lift it, and it doesn't really come off. And if I try super hard, at some point I got weaker. I couldn't do it last semester. So at least let's estimate how much force there should be here so that I don't feel like such a weakling. So what do you think this area is, approximately? Well, I guess we can measure it. Let me just measure it. It's a square of about, let's say, 0.25 meter on a side, 25 centimeters. So it's a quarter of a meter. So the area is 1/16 of a meter. Okay, or 1/20, let me just make it round numbers. Multiply that area to this pressure, then you'll get the force. What's 10 to the 5 divided by 20? So 10 to the 4 divided by 2. So 5 times 10 to the 3. 5,000 newtons. Is that a small amount of force or a large amount of force? It's very large. 5,000, it's a weight of a 500 kilogram thing. So, I mean, if you lift this hard enough, you will actually be able to lift it. And it's not because I can actually lift the 500 kilograms. If you watch it carefully, what happened is that this distorted enough that at some point it let air in. But yeah, atmospheric pressure is that much. Let me just show you one more demonstration to illustrate beyond any shadow of doubt just how big atmospheric pressure is. I can do it with a balloon and a vacuum pump. I have a vacuum pump here that can suck out all the air from this glass jar. And so normally we don't notice how big atmospheric pressure is because we have, I don't know, acclimated to it. Our own internal pressure constantly balances out atmospheric pressure. And and when I move my arm around, I'm not lifting all the air. Air kind of moves around me. So I'm not used to actually lifting atmospheric pressures. And to the extent that it's pressing down on my, all around me, I have developed a body structure that already accounts for that. It's like fish living in deep water. They are used to the great pressure in the deep water. So what I want to do is, I guess, what I can show you is put a little bit of air in this balloon and see if that's enough amount of air to make this balloon much bigger. So I don't really want to burst the balloon, so I should have put maybe this much. I guess it burst, it's not that big of a deal. All right, so you see there's some amount of air in here, right? Now, this is a question. The air that's inside here, is that enough to stretch this latex to fill up about this size of the bell jar? Let's give it a try. Right now, you say it's not. But here, right now, what you're seeing with the balloon is that the air that's inside is also fighting against the air pressure pushing in. So what I'm going to do is, I'm not going to put any more air in it. I'm simply going to remove the air around it, so that however much the air inside is pushing out will become evident just by itself. So there's nothing else that I need to consider. So let me turn on my vacuum pump. You're gonna see some smoke rising from that. It's because this vacuum pump is missing a part. It's just a oil mist. It's not actual smoke. It's harmless, and the person who'll be breathing it in most is me. So, all right. So I'm vacuuming it out. I want to stand far because in case that jar implodes, I want to be far away from the pieces. Oh, sorry, it blocked the hole. Well, yeah, that's the biggest problem with this. Occasionally it blocks the hole. Let me. No, it's gonna just. Okay, so I think what I need to do is I need to orient the balloon correctly. It's same pressure. It's not, shouldn't be sealed. I guess, so when I vacuumed it, something pressed it in, and you might have got it stuck. All right. Let me orient the balloon this way. That'll make it less likely that it'll roll over in a way that blocks the air flow. I really need a better equipment. All right, let's try this again. So vacuum it out. And this is actually a pretty good vacuum pump. It can go to a very small fraction of atmospheric pressure, like 1/100th of atmospheric pressure. Don't block the hole, don't block the hole, don't block the hole. All right, I guess that's good enough. Nah, all right. Let me just stop it here, because I guess it's not getting, did it block the hole again? What I think I can do is I can roll it over. I believe it'll be safe to have it tipped over on a side. So what I don't want to happen is for the glass jar to hit anything hard, because then it might break, and that would be dangerous. But I think what I'm doing is safety-wise okay. It's not tipping over enough to actually roll over. All right, let me keep vacuuming it out a little bit more. Did it block? All right. We'll just stop it here. But you can already see how much the balloon expanded. It has started out from the small volume, and it doesn't have any more air in it now than it does. What's different is that inside this bell jar, there's less air. So there's less pressure there. So the air that was originally inside the balloon was actually enough to make it expand this much. So, atmospheric pressure is one of those things that it's easy to forget how big it is, because in most circumstances, it kind of balances out. So we are used to thinking of atmospheric pressure as being inconsequential, but it's only because in everything we do, we have already accounted for it. And in fact, this is probably a good opportunity for me to introduce a particular phrase that's good for you to know. It's not something we're going to do anything with in this class, but if you ever deal anything with the pressure, like inflating your car tire or deflating a football, then this is a concept that's useful to know. Your textbook does talk about it. It's the idea of gauge pressure. Anybody here have heard the phrase gauge pressure? It's the difference between pressure that's measured in an absolute way and pressure that's measured as a difference. So this pressure here, this is an absolute pressure. The 10 to the 5 Pascal, that's how much pressure is here. But because that's such a large pressure and it's all around us all the time, to say that, I could tell you that there's a pressure of 10 to the 5 Pascal inside this glass dome, but that actually doesn't mean anything. I'm just saying that inside here, it's the same pressure as outside. So if you're, I don't know how much this is in PSI. Let me do the conversion so that I actually know the number in PSI. From alpha. So 10 to the 5 pascals in PSI. Pounds per square inch is another unit of pressure that you will see a lot, like when you're inflating your tires. So this is about 15 PSI, pounds, let me write it out, pounds per square inch. And if I said that your car tire inside has pressure of 15 pounds per square inch right now, I'm essentially telling you that your tire is not inflated at all. Because if you simply leave an opening, the pressure will equalize with outside, and it'll just naturally have 15 psi. So this absolute pressure, in many contexts, is actually less meaningful than stating the difference in pressure. That's where the idea of gauge pressure is useful. Gauge pressure. Gauge is actually the device that people use to measure pressure. And so this is saying the pressure you would read on a gauge. And most gauges work in a way that it measures pressure difference from outside to inside. So inside this glass dome, I cannot have absolute negative pressure, because I don't even know what that means. Negative force that's sucking things in, things only can push. But I can have negative gauge pressure, as much as minus 10 to the 5 Pascal. Or if I have a positive gauge pressure inside, that means things are trying to push things outside, and I would have to keep pressing it. So your car tires, like my Honda Civic, I think it's supposed to have 30 psi, and it would be 30 psi gauge pressure. So in terms of absolute pressure, it should be 45 psi. And this particular fact was useful. Couple years ago, do you guys remember the whole deflate gate thing where the New England Patriots were accused of intentionally deflating footballs to gain an advantage? That wasn't that long ago, right? It was only 2 or 3 years ago. You guys are alive then. No one here follows American football? Or football? Never mind. So there are actually some prominent physicists who are on TV talk shows saying how physics says the temperature drop wouldn't make the pressure go down that much, but they were wrong because they were mistaking the gauge pressure, which is how the football pressure is specified, with the absolute pressure. They were using something called the ideal gas law that you will learn in physics 4B. And all those laws of physics, it's stated in terms of the absolute pressure. But for measurement convenience, many things are measured in gauge pressure. And you should know the distinction between them so that you don't make that kind of mistake. Okay?
In this video, we will briefly talk about buoyancy force or Archimedes principle. So buoyancy force describes something that I think is familiar to all of us if you've been in water. When you jump into a swimming pool and you're floating, you feel like something is supporting you up. That's the buoyant force or buoyancy force. And the explanation for that is tied to something that we discussed earlier. We talked about pressure due to the weight of fluid. And that pressure, it changes with how deep you go. The pressure due to the weight of fluid increases with the depth. Or to put it conceptually, when you are underwater, there's a pressure pushing you from every direction. And in particular, the pressure that's pushing you downward from the top is not balanced with the pressure from the bottom. The amount of pressure at the bottom is greater because it's at a deeper depth. And the pressure, the expression that we looked at, given by the depth times the density of the fluid times g, this depth is greater. So that results in an upward force. Now, to work out an actual expression for the buoyancy force, it takes a little bit of algebra, and we won't do that. But what we can point to is something called Archimedes principle. This is something that a Greek philosopher named Archimedes figured out before we had all these Newtonian mechanics. It's a quite simple statement that's easy to remember, so let's just state it. Archimedes' principle says that the buoyant force on an object equals the weight of the fluid it displaces. These two are equal. So if an object is not in the fluid at all, then great. It displaces no fluid and there's no buoyant force on it. If it's completely submerged in water, then the amount of fluid it's displacing, it's the same volume of the fluid that would be there if the object wasn't there. So the weight of the fluid it displaces would come from the amount of volume times not the density of the object, but the density of the fluid. So from this dependence on the density, you can see that if you are dealing with an object that's quote-unquote heavier than the fluid, more dense than the fluid, then the buoyant force would be less than the weight of the object itself. In that case, the object sinks. Buoyant force is less. But if you imagine objects that float naturally on water, for example, like a piece of wood, it's less dense than water. So for those objects, it doesn't have to be submerged all the way. It can be partially submerged, and at some point, the amount of buoyant force through the amount of volume displaced would be equal to its weight, and it would stop sinking. It would float. Your textbook talks about specific gravity that's tied to this concept. You can take a look at that. For the rest of this infographic, as it says here, shape changes everything. So the amount of fluid that an object is displacing, it's not just the volume that it's occupying, it also includes any empty space inside. It's, basically however much fluid is pushed out from where it would be. So if you have a clay that's denser than water, it would sink if it's in a tight, compact lump. But you shape it into a boat, there's lots of empty space inside, then it can float. So this lower bottom, float over or sink, kind of gives those examples again. Most modern ships are not made out of wood. They are made out of metal, carbon fiber material that's heavier than water, but they float because there's lots of empty compartments inside with the air in it. Air's lighter. So when you look at the quote-unquote average density of a boat, it ends up being less than the density of water. Yeah, the average density. And this is used by submarine or fish to control the balance of the buoyancy force and the weight on them. So submarine has a ballast compartment that can be filled with water. So by controlling how much water is in there, a submarine can just rise without using any active propulsion. Or if circumstances demand it, they can fill that compartment with water to sink, again without using any active propulsion. And fish have an organ that's designed to do that. I forget the name of it. I'm not a marine biologist, so you can look that up. But there's lots of interesting examples of buoyancy force that we unfortunately won't touch on because we are going through this chapter really quickly. You can read about it, search about it on your own. I just want you to point out Archimedes' principle and just some basic things about buoyancy force. Thank you. In this short video, we will look at Bernoulli's principle. There's really one thing that I want you to take away from Bernoulli's principle. It's that it follows from law of conservation of energy. That is, Bernoulli's principle is the fluid mechanics version of statement of conservation of mechanical energy. So that actually means if there are things that might have led to the loss of mechanical energy, like friction in the context of fluid, then Bernoulli's principle will actually not hold. The exact same way mechanical energy can be changed into thermal energy when we are looking at conservation of energy back in chapter 3. And for some reason, it took several attempts to get Notebook LM to generate this infographic with that key information in there. Kept it getting distracted with other things. But let me just briefly mention, so when you have a fluid that's flowing, then different things can change. So as fluid flows, for example, the cross-sectional area of where it's flowing might change. Now, in those contexts, a lot of times you would keep the fluid flow rate constant, or you might just be more interested in keeping, how many gallons per second the same. In those cases, the narrower pipe forces the fluids to actually flow faster. That's what this equation of continuity expresses. It comes simply from what you might call conservation of volume. If your fluid is not compressible and there's the same amount coming in, then that same amount has to flow out. And the only way to get the same amount going out is to make the fluid flow faster if this area is smaller, or slower if this area is wider. Now, as these different things change, and also the height can change, here you see some fluid flowing down or some fluid flowing up. There are these different parameters relating to fluid that can change. And third and the last thing, the amount of pressure in the fluid can change. And that wouldn't be really easily seen, like, change of height or change of cross-sectional area can be easily seen. But if you have a, barometer or some other pressure gauge, then you can see how much pressure is in the fluid. And what Bernoulli's principle says is, as these different parameters change, we can combine them into this expression. I can write down this combined expression. Let me write it down here. The sum of pressure in the fluid plus this quantity that you can calculate, 1/2 density of the fluid and the speed of the fluid squared, the product of those three numbers, plus the density of the fluid times the gravitational constant, g, acceleration, 9.8 meter per second squared, times the height of the fluid. And these are all quantities that you can measure at a given point. So you might say pressure at point 1, density, let's say it's a constant. If it's incompressible fluid, it should be so. We'll say density is constant throughout the whole thing. The speed of the fluid might change, so that'll be at point 1. And then the height of the fluid might change at point 1. Bernoulli's principle says that this expression is constant. Or you could imagine doing this exact same set of measurements and calculation for a different point. You might measure pressure at a point 2, and you might measure fluid speed at a point 2 and calculate this 1/2 rho v squared. Plus, you might again measure the height of the fluid at a point 2, so rho g h 2. And because this combination of quantities are constant, what you calculate here for point 1 should be equal to what you calculate for point 2. And in the infographic, we associate two of these terms with something that you are already familiar with. 1/2 rho v squared, we associate that with the kinetic energy, and rho g h, we associate that with the potential energy. And I hope you see the resemblance. Before, when we were talking about kinetic energy, we looked at 1/2 mv squared. And for potential energy, gravitational potential energy, we looked at mgh. And so I hope you can see how there's that resemblance, that this is the fluid version of kinetic energy, and this is the fluid version of gravitational potential energy. Going from this amount of mass m to density, it's basically a difference between dealing with the discrete objects and the fluid element that can be infinitesimally small. So you have to deal with the density. But if you imagine, for example, multiplying this through by the volume of the element, then you would recover this. So in terms of conservation of energy based on conservation of the mechanical energy, kinetic and the potential energy, I hope that makes sense. And this additional term that you see here that the infographic labels pressure energy, I guess that could be a term. The pressure in the context of energy, it does occur in situations beyond the simple fluid mechanics. I guess what I would like to relate this to is the work done. And in a more mathematical class, I would try to derive this by imagining amount of work being done on a little fluid element, and that work being done could turn into kinetic energy, and it could turn into potential energy. And I would have a third term that tracks the amount of work being done, and that gets expressed in terms of the pressure difference. Or you can imagine rewriting this expression that I have written down here. You could rewrite it into this form. You can say the energy difference between the sum of the kinetic and potential energy at point 2 minus the sum of the kinetic and potential energy at point 1. Let me write that down. And when you finish doing the algebra, the change of mechanical energy is equal to P1 minus P2. And this is the term that you can relate to work done on the fluid. So as we talked about when we introduced energy, the idea of energy conservation, it is an abstract concept, and it can really only be fully explored mathematically. So I think this is as much math I'm willing to mention here. The main thing I want you to remember is that Bernoulli's principle comes from conservation of energy. It's the fluid version of conservation of energy. And more mathematical details, when and if you take physics 4A, you can see it there. For the purpose of this class, we'll leave that there. That this is something that that applies to fluid mechanics, and there are interesting examples of applications of Bernoulli's principle. I think with the amount of time we are spending on this, which is not a lot, we don't really point out those. I think one of those applications are spelled out here. So key consequence where speed is higher, pressure is lower, and there are fun demos you can do using that. But again, with the amount of time we are spending on fluid, we are not really gonna do that. You can look up, Bernoulli's principle demonstration. I'm sure there are YouTube videos illustrating that. So I'll just leave this here. Thank you.